beginning of the series in 2014-15 of CP3 lectures. This weekend we have Chun from the Korean Institute for Advanced Study. For the people that don't know, we actually have a working relationship with KIES. So if they're interested in visiting KIES and vice versa, we're also going to have basically also visitors from KIES. Another young postdoc soon. So you just should let us know, and we could of course find a way to make that possible. There's a lot of overlap in phenomenology that we would like to further exploit. This is actually very interesting from the fact, and also cosmology and other sources like for some of you who are interested. So it's a pleasure to have Chun visiting us and for this week, and talking today about Axino phenomenology in the Kim-Nilles mechanism. Thanks.
Okay, thank you. Okay, it's my first visit to Denmark, and I'm very happy to be here to see this active history group. In fact, we, as Francesco said, KIAS and CP3 has an MOU, so on the which you can visit us, and we provide you local expenses. Probably, fairly provide Francesco. Okay, so last week of this October, we have annual phenomenology workshop. So Francesco is coming. If anybody else is interested in coming, please let us know. Okay, so today I'm going to talk about Axino phenomenology. I mean, I've been working on this topic since many years, and then recently there is some kind of revised interest. And then, okay, the first, say 15 minutes, I was asked to give some review in the introductory talk. So I will spend the first 10 to 20 minutes explaining what the axion, what the strong CP problem, and what the axion is. And then I go to the in this case we have two kinds of typical axion models. And then I will explain them. And then, so now we go to supersymmetry to include axion in the context of SUSY. Then the superpartner of axion is called Axino, the fermionic partner. So the Axino cosmology and phenomenology is the main part of that. So I particularly concern on the scheme of natural SUSY in view of Kim-Nilles mechanism. And there, I mean, my conclusion will be that we must have mixed Axino-axion whole dark matter. Then, well, this is the case where Axino is heavy and unstable, but also the Axino can be there at speed.
Question. Is Kim-Nilles and Kim-Nilles Peloso, are those different mechanisms?
It's different. Kim-Nilles Peloso. Oh, that's yeah, that's.
Okay, that's the aligned axiom.
Yeah, this is about inflation, but this is very old one.
Okay.
1984.
Okay.
Yeah, I'll explain. Yeah, this Kim-Nilles Peloso mechanism is more popular, right?
Yeah. Sure.
In the bicep too. Okay, then I will talk about the LHC phenomenology of Axino with the Axino LSP, also in the context of natural, so-called natural SUSY. And I conclude. Basically, my talk is based on these four papers, three about Axino and SUSY Axino stuff, and the last one is about the LHC phenomenology. Okay, so let me start talking about U1A problem of QCD. So this is QCD Lagrangian. So, and then if we take some of the fermion mass is 0, then we have, definitely, we know that the up quark and down quark masses are very light compared to the typical QCD is scale. So we can treat it as a massless particle. And then in this case, we have U2 V cross U2 A symmetry. So we have two flavors, massless two flavors, then arbitrary phase, rotation of these two is a symmetry. So we have U2 cross U2 symmetry. So I mean, the U2 rotation and between this U and B quark, and another U2 for the rotation of UC and DC core. So this U2V, under this U2V, this mass operator doesn't change. So it has, say, charge +1 and antiparticle has charge -1. So this is invariant. So this is a good symmetry, even in the case of massive quarks. But U2A acts like this. So say Q +1, QC +1. So after this rotation, you get phase in the mass. So this is not conserved. It's not a good symmetry if there are masses. But still, in the massless limit of U and V quark, it's approximately good symmetry. So because of that, we have this good description that the pion can be considered as a pseudo-Boston boson. And okay, so basically U2V can be composed as U2V cross U1V, which is nothing but the baryon number. So baryon, you know that baryon number is conserved in standard model. And then proton neutron are SU2 doublet and pions are SU2 triplet. This is a good symmetry. The baryon and meson vector. Now, this must be U2. So U2A also has a SU2 part and U1 part. And then this is broken by QCD condensate. Right? So stone QCD will develop non-zero wave for this operator below the QCD scale. Then it breaks this U2A symmetry. So as a consequence, we should have a massless Goldstone mode, say 3 massless fields from the breaking of SU2A, and then 1 massless mode from the breaking of U1A. But in reality, this pion, you know that it's almost massless. It's very light compared to the proton and neutron mass, or the hadron state, which is around 1 GeV. But eta prime, but we don't find such light state, which must be must correspond to the Goldstone version of U1A break. So in fact, we have eta prime, which is a scalar, but this mass is compared to the proton neutron mass. It's much heavier than the pion mass. So this was a puzzle. When you have very good, effective description of QCD, the mesonic state after QCD condensate, but in nature there is no such light meson field. So then Weinberg realized that this means that the eta prime, this U1A problem was recognized by Weinberg, and then its solution is to the so-called ABJ anomaly. So in fact, we know that the U1A is not a symmetry. So if you have axial current, then take a divergence, and then you calculate the loop diagram, you know that this is anomalies. So after some calculation, you get that the divergence of axial current gave rise to this GG dual terms. So this 2NF is the anomaly number of this axial symmetry. I mean, basically, it is number of quark fields circulating the loop. So we have UC and DC. So we have, for each we have 2. I mean, in the case of UD massless quarks, we have 4. The anomaly number is 4. Now, so we take this U1A rotation, then typically we have this kind of behavior, and then so due to this equality, we can take the right-hand side. So we are having this integration, And then this volume integration turn into the surface integration that, I mean, okay, so this is GG is basically expressed in terms of so-called value K-mu, and the K-mu is this Chun-Simons curve. Then the SU3 structure, so there are certain configuration that this surface integral gives you the some topological quantum number, so called Chun-Simons number. So then this is obviously non-invariant. So the U1A is not a conserved symmetry. It has anomaly, and then this quantum anomaly breaks this U1A. Now, because of this, this QCD must have some unique vacuum structure. So, so this Chun-Simons number corresponds to some certain configuration of a pure gauge configuration. And then Chun-Simons number 1 means that this is trivial gauge, which can be shrink to, which can be connected to the identity transformation. But at the infinity, usually we forget about this surface integral at the infinity because, you know, so we usually assume that this kind of any physical quantity should be vanishing at the larger sphere. So, but in the case of SUC structure, there can be some non-trivial topological configuration which doesn't vanish at the infinity. So then we have this, this is called say n vacuum configuration. So for each topological quantum number n, we have this is kind of winding number configuration. So different such a pure gauge configuration which has different quantum number n. Now, so once we have this n vacuum, then we can take some say SU3 transformation. Then this transformation can transform the n vacuum quantum number to n plus 1. So this is again, this is a pure gauge transformation. So this n vacuum is not gauge invariant. But if you take this combination, so you see that this is gauge invariant. So this must be the true vacuum of QCD. So effectively, what you have is that you have to include this GG dual operator with some constant theta in your QCD Lagrangian. So when you take say the path integral of all gauge configuration, you get some say gauge invariant measure. Okay, so well, this way from the non-symmetry property of U1A, we learned that we must include this theta term in QCD Lagrangian. So and then of course there is well, this is GG dual term is also SU2 gauge invariant. So we can put we could have put by hand in the beginning. Now the trouble is that again then this is a CP odd operator. So you know that QCD is a CP converting, but this theta term violates CP. Then because of this CP violation, it can induce, say, a neutron EDM, which has this form. Now, current experiments said that this neutron EDM is very, very small. And then from which we can conclude that the theta must be smaller than, say, a few times 10 to minus 11. So this is currently. Okay, now you have to ask then why theta is so small. So in particular, compared to the weak CP, which is order 1, the strong CP must be very, very suppressed. well then this can be another kind of hierarchy problems in standard model. Say, you know that top value bar is 1. The neutrino power must be very small if they are dark particles. And also there is some zeta problem. It's a strong CP problem that why we have to understand why zeta is so small. Of course, if you like, you can just put so small number. But there is a nice dynamical mechanism to explain that, which is due to the axion field. Okay, actually Petrarchin solved this problem by introducing some spontaneously broken QCD anomalous global U1 symmetry. Okay, so yeah, first of all, this must be global, and then must have a QCD anomaly. And then after spontaneous breaking of this, we must have the Goldstone boson, which is called axion, so corresponding to this symmetry breaking direction. Okay, so there are two ways to implement this Petrarchin symmetry. One is that the so-called Kim-Nilles-Zakharov mechanism, that we introduce some very heavy quark field with some extra quark, vector light of quarks, and then we assign some U1A, again U1A kind of symmetry. So we assign different U1 for quark and anti-quark. So S is carrying some U1 charge. Now, after this U1 symmetry breaking by the web of S, which is called the VPQ, the axial field of this A is the Goldstone boson. Right? So this is one way. And in this case, number of QCD anomaly is nothing but the number of these vector-like quarks. Now, the more minimal way would be extending the Higgs sector. So here we introduce a singlet field S carrying, say, Petrarchin charge. We assign the Petrarchin number for HU and HD minus 1. This works for two Higgs doublet models. So, and then we can assign a PQ charge -1 for HU and HD, and then 1 for S again. Then see again the assigning PQ charge 0 for quark, the doublet quark, you can assign 1 for UC and 1 for DC. This is again chiral and axial current, which must have QCD. So in this case, if you count the number of PQ charge carrying fields, this must be 2 times n. One from UC, the other one from DC. So in the DFSZ, in the case of two generation, we have anomaly number 6. Okay, now, so in this case, Higgs field also carries Petrarchin symmetry. So, and then after electric symmetry breaking, so this quark mass operator also contain this phase field into the IA. And then in the case KS VGK, this is so-called also heavy quark axion model. So the mass operator after PQ symmetry breaking scale contains this phase field, the axion field. Now you rotate away this axion field to make the mass matrix real. Then this is another symmetry. Then due to anomaly again, we pick up this A-GG dual interaction terms. Okay, so the phase field in the mass matrix goes to A-GG dual. Okay, so in the beginning we had some constant gauge invariant parameter, and then having spontaneous broken Petrarchin symmetry, we can have this dynamical degree of degree axion talking to GG dual again. So now we can define all of these two combinations as effective theta term for just axion field. Okay, so actually this GG dual with this normalization, so usually people put the axion decay constant FA here, which is nothing but the VPQ divided by QCD anomaly number. And this is also so-called domain volume, which I'll explain later. And then after the QCD phase transition, we know that the QCD instanton effect generate action potential of this form. And basically theta is, this is a pure variable. This is nothing but the phase field. So it must have this kind of symmetry oscillating behavior. And then by minimization, this has to settle down to 0. So this is now a dynamical field whose web must be 0. So in this way, the effective theta term must be 0. So this is called the dynamical relaxation of theta. Okay, so theta bar here is nothing but A over FA. So by taking the quadratic term of axion, we get the axion mass like this, lambda QC squared divided by FA. Now since we know the FA must be very, very large number, like around 10 to 10 GeV, the axion must be very light. So lighter than 10 to minus 3 electron volt. Okay, so in fact, when Petra, Kim, and Weinberg wrote their first model of action, they thought of having, they had this 2 Higgs double model plus PQ charged singlet field. Then they thought of the PQ symmetry breaking scale around Wick scale. But immediately, this low PQ symmetry scale is ruled out by various the collider experiment. And then nowadays there is strong lower bound coming from the star cooling. So axion is the Schuder-Goldstone boson interacting very weakly. So once this is produced in the star, it can just escape. So it changed the history of star cooling. So that then the production cross section must be very suppressed, meaning that FA must be very large. And then this gives lower bound like a 10 to 10 GeV. And the upper bound comes from axion dark matter density. Being a scalar field having some potential like this, initially this axion field can start to oscillate at certain non-zero value in the history of the universe. Then it can oscillate. And then typically we can expect to have this initial value around the PQ symmetry breaking scale, FA. So then at 0 temperature it oscillates, and then it will settle down to 0 at low temperature. This is a zero vacuum value, but in the early universe it can start from a non-vanishing value, and then it oscillates and give rise to cold dark matter. So from that we get the usual bound of 10 to 12 GeV in order not to overclose the universe by axion density. So this is a typical range of the PQ symmetry breaking scale, so 10 to 10 to 12 GeV. Of course, depending on how you calculate the axion relative density, this number can vary, can change. Okay, so another important topic in this axion analysis density is that so-called domain wall problem. So if the QCD anomaly number, which is nothing but domain wall number, is less than 1, that means that there can be n-1 different vector inside the theta vacuum. So then there can arise some topological effect called domain walls connecting different vector. So then, of course, it is stable and then overflows the universe. So remember that I said the domain wall number is 1 for the minimal KSVG and then 6 for DFSZ. So if the Petrarchan symmetry is broken during inflation, you don't have to worry about the melon problem, right? So inflation dilutes away everything. But if PQ symmetry is broken after inflation, you must have a domain on number 1. So in this case, we should take a KSVG model with only one vectorized external parts. Of course, in this case, you can also deform DFSZ model to make domain on number 1, or there could be some slight breaking of PQ symmetry, which make the domain unstable. There could be many ways to avoid this domain number problem. But in the minimal scenario, the simplest way to get domain number 1 is to take the simple the minimal KS3G. Okay, so I mean, this is a more refined calculation of axion relief density. So here it contains these two parts. So one is the usual coherent oscillation production, and the other one is so-called ice curvature production during the inflation. So before I didn't mention, but during in the process of QCD phase transition, there could appear topological, say, structure like axion string and domainers. So in the case of domain number 1, they can decay to cold axions. So that and depending on there have been 3 different groups trying to calculate what will be the resulting axions coming from the topological defects. So, for instance, most conservative number 1, I mean, the Skibby group claimed that this topological defect contribution is negligible. And Japanese group claims that this is must be a factor 10 enhancement. Then there was some other group claiming that this can be as large as 100. So I cannot judge. But the Japanese group refined their calculation over and over. I mean, they are the only group who keep. I mean, as computer power increases, they try to put this computation in a simulation, and most recently they claim that this number should be between, say, 10 to 20. So if we take this number 10, and then if the PQ symmetry is broken after inflation, so this theta, initial theta, should be averaged out. I mean, each component of the universe patch can have different theta value, so we just take average. Then this is typically this number, so which is about factor 10. And you put the topological defect contribution around factor 10, then this is a factor 100 enhancement. So in this case, then the FA should be smaller than a few times 10 to 10 GeV. So FA is smaller than 10 to a few times 10 to 10 GeV is the advocate number by Japanese. Of course, if a PQ symmetry is broken during the inflation, you don't have to worry about this. Just you can take the arbitrary initial condition of theta 0. So one small patch of the universe expanded to make the universe rearranged. But in this case, there can be since axion is very light, there can be the quantum fluctuation, which must have this kind of size. Now let's take FA around 10 to 10 or 10 to 12 GeV, and then Hubble parameter during the inflation, I don't know, 10 to 14 GeV. After bicep 2, then this is a huge number. So that if bicep 2 is right, then basically PQ symmetry breaking during the inflation is ruled out. That means this large ice curvature operation. And of course, there are some ways to avoid this conclusion.
Sorry, this comes only from the isoperimeter?
Yeah, yeah.
Only from the other modes? Oh,
That's
sorry,
right.
only from the spectral index or from also the tensor modes? Because I mean, what the facet 2D was basically in principle to increase the tensor modes, right?
Yeah.
Not the isoscalar conditions, but basically.
Yeah, that's, I mean, okay, this isochromatical constraints comes from Planck.
So you're saying
So they measure the Planck limit for isochromatic perturbation is say or 1% of scalar perturbation,
Right.
so which is very strong.
Yeah, I don't know.
Yeah.
So this also basically is the fact that basically this should be Planck, gut scale.
FA.
No, yeah.
Yeah, if FA is say. I mean, to avoid that, basically FA should be very close to Planck scale. Then you can avoid this. Maybe. Well, the one scenario I wrote about is that during the inflation, actually the PQ symmetry frequency can be much larger than the current value, which is kind of natural in particular in the context of supersymmetry. So in that way, you can avoid size curvature. Okay, so this is probably the end of the introduction part. Any questions?
Sorry, in this case, so there is no, what is the room for FA? Because if you really get more seriously advanced from this, then there is no much room left for the axion. If you take seriously the cosmological constraints, because before the cosmological constraints, FA can be between 10 to the 10 and 12 J. Apparently, if I take this into consideration, then there isn't much room left, because in one case, I'm actually...
Okay, so yeah.
I'm just
let me summarize. Yeah, that's right. So, taking the typical range of FA, say 10 G-ish, then PQ symmetry breaking during inflation is ruled out. Then PQ symmetry must break after inflation. So taking this number alpha around 10, then FA should be around a few times 10 to 10 G.
So which is, so that the second option is, still with...
Yeah, that's right.
Okay.
With domain number 1.
Okay, fine. So, but yeah.
Yeah, that's the standard prediction of the FWZ. Right, and now let's go to the supersymmetry. Supersymmetry action model. Of course, it's straightforward to supersymmetrize the previous KS region DFSZ. So instead of scalar Quark operator, you introduce the superpotential. Again, the peak numbers are the same as before. So the QCD anomaly number is the same. And in the case of DFSZ, we can also introduce this dimension 4 operator in the superpotential. Now, after PQ symmetry breaking scale, this can generate so-called the new parameter of Axino mass term. And then taking S around, say, 10 to 10 GeV or 10 to 11 GeV, depending on your choice of lambda, you can see that this mu number can be at the electroweak scale. So this was noticed by Kim-Nilles in 84, of course. So this is so-called the Kim-Nilles mechanism to explain the mu problem of MSSM. So DFSZ, this is nothing but the DFSZ realization of action model. So I mean, in this way, we can solve strong CP and mu problems simultaneously. So this is, I like this option very much. So that's why I'm working in this model. So now, so we have supersymmetry. So the axion field has its companions in scalar part and fermionic part. So we call it section, and this is Axino. And after the PQ symmetry breaking, we have effective theory, MSSM plus axion superfield. So basically, the section and axino play important roles in cosmology, including the diagonal properties. So in the KSVG supersymmetric axial model, typically axino and section coupling come only from this, say, A GG operator. So this is supersymmetric component of A GG dual. So axino, gluino, gluon, and section, and gluon, gluino. Gluon, GG dual. Yeah. No. Oh, this must be SGG, not GG. So this is dimension 5 operator suppressed by 1 over FA. Now in the case of DFSZ, the axino couples to Higgs and Higgsino from the mutum operator, and then its coupling is like Yukawa, say mu of FA. This is small Yukawa coupling, which is taking mu 100 G, FA 10 G, this is over into minus 8. So very, very small Yukawa coupling. Of course, since we have also axion top interaction, also axion can couple to top and top, etc. So in this case, this interaction is proportional to top mass, and for mu Higgsino case, this is proportional to Higgsino mass mu. So these two models have this characteristically different coupling structure. Okay, now axion and section in the context of supergravity theory, well, their mass is quite model dependent. So one of the typical ways to break PQ symmetry is to introduce this kind of potential, superpotential. And then, well, S carries PQ charge 1 and S prime minus 1. And so from this you can, so if you minimize scalar potential coming from this potential, you get that the S valve should be, and then S prime valve should be around FA. And then if SUJI is exact, X doesn't get FA. But in supergravity or any SUJI breaking, there could be SUJI breaking terms, soft terms, and then you can lift the valve of X to around, say, SUJI breaking value. So, and then this valve gives the mass to Axino. This is a supersymmetric mass term if X gets back. So typically the Axino mass is determined by the coupling times this.
So just to be precise, this is the theta square, this is the F thermal X, I guess.
And this is.
In order to break SUJI.
Yeah, that's right. Yeah.
The theta must be the F term.
That's right. Yeah. Exactly. So take F term from SS prime, we get fermionic phase, the mass of fermionic phase. Of course, depending on this, how you break Petrarch symmetry, this could be, so suppressed. So we imagine some complicated symmetry breaking better. Well, and then you can play with this parameter lambda, so basically the axional mass. Well, typically we expect that this should be around the gravitational mass.
Sorry, so who is S prime? So S is the Petrarchian.
Yeah, this is Petrarchian.
And S prime is another of these?
Yeah, this is, okay, so here you introduce S having Petrarch charge 1 to realize GCD Yuan symmetry. But yeah, this is typically, this is a vector-like pair. So carry 1 and minus 1.
So you have both.
Yeah. This is
So S prime is ST then?
yeah, this is anti.
Oh, it's compass.
anti superfield. Okay, so I mean, okay, and then of course, if you have some model where X web vanishes, then there can be also loop generated axional mass from this operator, and then it can be also suppressed. But section mass, you know, must be section mass should be around gravitino mass. This must have a soft mass squared contribution. Okay, now, as I said, let's consider the cosmic axino and section production. So, although the axino interaction with ordinary fields, say quarks and gluons, are very small, still, so typically axino or section cannot be in thermal equilibrium. But they can be produced from thermal particles interactions, right? So the gluinos and gluons and the quarks and sparks are in thermal equilibrium, and then they scatter to produce action abundance. So then the abundance of section on axino, I mean this Y number is typical number density normalized by entropy density. The Horton equation follows this form. And then typically for KS3G having dimension 5 operator interaction, the cross section this probability is suppressed by 1 over FA. So I mean this whole quantity is proportional to this number. Then DFSZ we have U-car interaction, mu over FA. So that in this case, this operator is suppressed by 1 over temperature squared. I mean, this is nothing but, I mean, this is similar to the gravitino production. So you just integrate out, then the KS3G axional production is proportional to the highest temperature of the universe. But in the case of the FSZ, I mean, this is the case whenever you have U-car type interaction, small U-car type interaction. The final abundance is proportional to 1 over T, the lowest temperature you get. So taking T, then T must be larger than the section or axional mass. Then so the lowest value for T could be, say in this case, Wick scale. Okay, so because of this, I mean, okay, so the precision calculation was performed by many groups, and then, well, this is typical precise number. This is just from Strumier. Then taking 10 to 11 G of action scale, re-temperature TeV, in order not to overclose the universe, axional mass is more than 40 MV. So DFSZ, so typically we have this kind of interaction scattering rate. Then say taking again same FA 10 to 11 GeV, mu parameter 10 TeV, and say the lowest temperature, say T around MH, which is TeV, then the stable axional mass should be smaller than say 40 keV. So if axional is stable, so their mass must be very, very small. So in case of KSVG, if you take the real temperature, say 10 to 10 GeV, then axional mass should be tremendously small. And then here is another important thing is that this number you have to memorize. I mean the Y number for axional thermal production is around 10 to minus 5, which is huge number. Although their interaction is suppressed by mu over FA, which is a small number, their thermal generation is very effective. And then of course the reheat temperature of the universe is much smaller than say typical L to weak scale. Then the Axino production must be Boltzmann suppressed. In that case, you can allow larger mass. So this is one of the typical calculations. And then here so Axino can be produced by decay and inverse decay and scattering of thermal particles. And then taking Fa 10 to 11 GeV, independent of TR, we can have Axinoid around 10 to minus 5. And then for smaller TR, this is Boltzmann suppressed entail. So the Axino yield can be, of course, Boltzmann suppressed. And in certain case, there can be resonance scattering. Say if Axino and initial particle masses same as 2 times this S-channel particle mass, then you can have some resonance enhancement of Axino. But typically, so we have say 10 to minus 5 Axinoid for this range of particles. And then for the case of a section, as being a scalar field, you can also have coherent oscillation production. So this can be, depending on your parameter, this can be much, this number can be much larger than this number. In particular, if Fa becomes larger, this coherent production becomes larger, but this thermal production is suppressed. So it goes to the opposite direction. Okay, now, once we have a supersymmetric axion model, so Axino and section population is huge in the early universe. And then as a consequence of that, you must have either very light Axino or very heavy Axino decaying promptly. So we have to worry about what are the effects of section and Axino decay. So for the case of section, you can decay to 2 axions that will contribute to dark radiation. Also, this decay rate is given by this PQ sector parameter. So this is also model dependent. So basically, Cauchy controls the size of the decay rate of section going to 2 axions. And then this is not the supersymmetric counterpart of 2 axion production, and this is 2 axional production. And then in the case of DFSZ, we also have a section go to 2 Higgs or 2 axions from mu-term interaction or B-term interaction. And then Axino can decay to Higgs and Axino through those of the mu-term interaction in case of DFSZ. Okay, so then in order to see the effect of section and axional decay, it is important to see what is the decay temperature of section and axino, which is just the square root of decay rate times m prime. Then taking Fa 10 to 12 GeV, mu say 200 GeV, the decay temperature is 1 GeV. So then, okay, so now in the universe we have so copious production of axino and sections, and then their decay can produce, a huge number of usual neutralinos and the relativistic axions, and then also you can also dump a huge number of entropy as well if they decay too late. For a large Fa. So all this will affect the standard cosmology. Okay, so one important application is that its impact on neutralino relic density. So as I said, the Axino yield is around 10 to minus 5. Then if decay temperature of Axino is larger than the freeze-out temperature of your neutralino, typical neutralino, SP, then of course this is before freeze-out, so the produced neutralino will summarize among themselves. So the final relic density of neutralino will just follow the standard freeze-out relic density. But if the decay temperature is smaller than the freeze-out temperature of neutralino, then so after freeze-out of neutralino, the Axino or section decay dump a lot of the neutralinos. Then there is a chance that they can reannihilate among themselves. Since we dump a huge number of neutralinos, even after freeze out, they can annihilate to ordinary particles. So, so this is a reannihilation of neutrino, reannihilation mechanism. So in this case, the final relic density of the neutralino SP is determined by this formula. So in the usual freeze-out case, instead of XF, we had instead this XD is nothing but the neutralino mass divided by decay temperature. So in the standard freeze-out case, we have XF. So XF is mass divided by freeze-out temperature, you know. And then its number density is inversely proportional again the annihilation rate. So I mean, if the annihilation rate is too large, typically we have too small relic density. But in this case, the Axino decay temperature is much smaller than the freeze-out temperature. This XD can be much larger than XM. So even with the smaller, the larger annihilation rate, we can have right neutralino down matter rate density. So I mean, this makes Reno and Hixino a proper down matter candidate. Okay, so now so I can go to the main topic. So one of the application of this Axino phenomenology is to say so-called natural Suji. You know, in Suji we have this so-called naturalist problem that the minimization condition of this scalar sector of Higgs has these two kinds of conditions. Has to satisfy these conditions. So if you look at this, the G boson mass is correlated with the 2D parameter mu, and then soft parameter, soft masses of HU and HD. And the Higgs mass itself, so we have a 3 contribution, which is smaller than say 90 GeV, and then there can be sizable the stop or spot-to-Monod coefficient, which can have sizable contribution to explain the observed value. So for this, I mean, so far we LHC didn't find any say squawks or gluinos, and then the current mass limit is say 1 or 2 TeV. So on the other hand, this value is good. I mean, if a stop mass is around TeV, we can have right Higgs mass. So taking say the maximal mixing of stops. So I mean, this is the mixing mass contribution. So for large X, we can have right Higgs mass in this column. So for taking star mass around the TeV, we can have right value of Higgs. Well, this is standard scenario in supersymmetry. Now, still, I mean, having multi-TeV region of soft SUJI breaking, this make the electroweak symmetry breaking unnatural. Taking large tangent beta, the one of the minimized condition has this simple form, and then so taking TeV scale of soft mass, so we need to have some fine cancellation to get the 90 GeV G boson mass. So now here is a claim to make it natural. Say this is so-called relatively driven natural SUJI. So there are notice that the fact that so we start with very certain value of heavy, say multi-TeV soft parameters at first scale, and then you run them down. Then MHU squared gets negative at low scale, right? Due to large top conjugate effect. Then you can make this MHU squared around weak scale in size. And then so mu is another independent parameter. Then also to make it natural, say not too far from mg, then we also want to have mu around say 100 GeV or 200 GeV. So you don't want to have a much larger value of mu and rely on some fine cancellation between these two. So yeah, there's kind of mass spectrum realizing this. And then, so this is one of the benchmark point, so-called SUA, meaning standard underabundant scenario. So here they start with this initial value of M0, M1/2, A0, tangent beta mu, the first scale, and then you run them down to get, say, Higgs mass 125 GeV, etc., etc. And then now you have this small variable mu, and then Axino now is the NSP. So the so-called this natural SUJI, taking natural SUJI means that Axino is the lightest component of SUJI spectrum. Now Axino has a strong gauge interaction, the SU2 gauge interaction, so it has large annihilation rate. So typically their relative density is 10% of the usual required relative density point omega h squared polygon 1. So you cannot then it just consists of 10% of required weight. So this is so-called underabundant scenario. Okay, so now, so we apply this natural SUJI in the context of Kim-Nilles mechanism. So we combine this natural SUJI mass parameter region with the supersymmetric DFSZ model. And then in this case, we have of course three kind of Dangler candidate, Axionos, which is typically underabundant, but re-annihilation can make it 100%. Having XD rather than X. Then axion, of course, there is axion, so it can be also Dangler candidate. And then Axino, also Dangler candidate, it's very light. But these two are contradictory. So either you have Axino Dangler candidate or Axino Dangler candidate. You cannot have both. Okay, so we took this benchmark point in the Kim-Nilles mechanism, and then assuming certain Axino and section mass, say 5 TeV. So we calculate the say Axino Dangler component and axion Dangler component here, depending on the Petri-Pin scale FA. So it has typically three regions. So for FA smaller than say Okay, so the dotted line are for Cauchy value 0, meaning that the section cannot decay to 2 axions. And Cauchy equal to 1 is the maximal decay of section to 2 axions, 2 dark radiation. So here, if the PQ scale is smaller than, say, around 10 to 12 GeV, then the axion or axino decay is effective. So decay temperature is larger than the freeze-out temperature. So the Higgsino dark matter component is the standard value, so 0.01. Okay, now then what can we do with the other 90%? So we just add axion component. We just take some appropriate value of initial theta and so on. Of course, this is also cosmology model dependent, but there is axion which can cover the 90% of missing dark matter component. Now, for larger FA, larger than 10 to 12 GeV, the decay temperature of axino can be larger than the freeze-out temperature. Then reannihilation mechanism can apply, so that the Higgsino relic density increases. Okay, then normally it should go like that, but in the case of Cauchy equal to 1, basically the first rise is due to axino production. When Cauchy equal to 1, section usually go to 2 axions. So in this part, the section decay doesn't contribute. And then for larger FA, axino contribution becomes negligible. Then again, the section component become more important. I mean, this is due to coherent oscillation of section density, which becomes larger for larger PQ scale. So we can have this kind of behavior. From this, so we can set the upper limit of PQ scale, so it's around 10 to 13 GeV, in order not to go closely with this. For Cauchy equal to 1, or for Cauchy equal to 0, a few times 10 to 12. Okay, so in most regions, I mean, we can have an interesting mixture of dark matter, say axion plus Axino. So 90% of axion or 10% of Axino, or even say in this case 10% of Axino and so 100% of Axino, and then any mixture in between. Okay, so then, so this is nice that we can have either Higgsino detection. We can have both the Higgsino detection and axion detection in the future. But this is the current axion detection coverage at the ADMX. And then the future limit are here. But it probes the Petrarch scale around 10 to 12 GeV. And this one. And then as I said, so after bicep, if we take the PQ scale a few times 10 to 10 GeV, the axion mass should be around this corner, which is far from the current sensitivity region. So, it would be nice if we can have another experiment which can be sensitive also in this region. I'm not sure whether this is technologically possible in these days. So let me just advertise one thing that, and recently the new axion experiment is set up in Korea. And then they will do the similar experiment like ADMX. So I hope they can somehow cover this corner. That would be nice. But I don't know. Okay. So last topic, the LHC signature of the Axino LSP. So now let's assume the Axino is the LSP. So what can happen in the context of natural Suji? So as I said, natural Suji means that the Axino is supposed to be lightest component. And then if Axino is lightest, then the charged Axino, this charged Axino and neutral Axino are almost degenerate. It has very small mass gap. Then the charged Axino will decay to say pion and then the lightest one to official W plus minus. So since this is too soft, we cannot see this pi plus minus production at the LHC. So the basically natural Suji spectrum is very hard to probe. And then okay, so there could be a possibility that the Bino is even lighter than the Axino. The Axino NLSP around 200 GeV, Bino say 50 GeV. Then in this case, the charged Axino can decay to W plus minus Bino, and then neutral Axino to Higgs or G plus Bino. So as we did the exercise, I mean, actually the current atlas looks for the trileptons plus missing ET to constant the Vino-like dark matter. To see the Vino-like dark matter. So these are the current. This is the current limit. So x-axis is the mass of NLSP, and then y-axis is the mass of the LSP. Taking the very small LSP mass, the current limit for NLSP mass is about 350 GeV. So this is the case of Vino NLSP. Then we just apply this calculation to Axino NLSP case. Then again, mu up to 250 GeV is excluded. So in this way, so natural Suji region can be proved. Of course, it all depends on the mass gap between NLSP and LSP. Now, what if the Axino is the LSP, Axino is the LSP? Then again Axino interaction is suppressed by 1 over Fa, so it can decay very late. I mean, Axino can decay very late to Axino. So typically we have displaced vortex from Axino decays. So here we calculate the decay gap, decay length of Axino, taking Fa say around 10 to 9 GeV. So this line, depending on the mu parameter and Axino mass, this line is 10 meter of decay length, and this is about say 600 micrometer of decay length, which can be probed. So any decay length between these two can be probed by the current LHC experiment. So meaning that mu around 300 GeV can be probed. Of course, for the case of PQ scale 10 to 9 GeV. For higher PQ scale, I mean the decay length is proportional to the PQ scale squared. So you can, this region can shrink down. Okay, so this is our result. And then the CMS looks for digest displaced vortices. So we translate their result into our Axino system. So then of course, I mean, it all depends on the so-called the efficiency of displaced vortex tracking. So, I mean, this is experimental number which we don't know. So we just took the optimum, I mean, any number between 0.1 and 0.01. So if the efficiency is very good, then see, you can cover the PQ scale from say 10 to 9 to 10 to 11 dB. So this region is often view around 350 GeV. So depending on the sign of mu, the excluded region can be slightly different. And then this region is excluded by, say, prompt the Axino decay, which occurs for the PQ scale below 10 to 9 GeV, which is not interesting for. I mean, it's already. I mean, the PQ scale must be less than say 10 to 9 or 10 to 10 GeV. So that this is just for illustration. So we are more interested in this displaced vortex storage. So this calculation can be projected naively to LHC 14. So we don't know what will be detector for performance and what will be the other background like. But we just assume that the same kind of efficiency, and then we just scale up the cross section, and you can also send the same detection property, so that okay. So this is LHC 8 in number. So so this is excluded number of PQ scale as a function of mu parameter on the x-axis. So taking axional mass around 0, very small axional mass, actually we can exclude PQ scale around 10 to 11 GeV. Again, assuming the efficiency factor of 0.1, which is optimistic. So LHC 14, we can go to close to 10 to 12 GeV with 1 inverse 21 of total velocity. Okay, so then, so to exclude FA, let's say up to 10 to 12 GeV, which is the typical the upper bound, and then so we have to have one autobahn. We may kill this scenario, Axino, and LSP, Axino, LSP scenario. Okay, now let me conclude. So resolution of the mu strong CPM Higgs fine-tuning problem may indicate the combined scenario of natural SUSY plus DFSZ axion model in supersymmetry. So then, the long-lived axions and sections can be produced copiously to change the cosmology. So in the case of heavy unstable axino, their late decays may produce a significant amount of neutralinos, dark radiation, and entropy. So although I didn't talk about anything about them, and to change the dynamic cosmology. So taking some typical scenario of natural SUSY, we conclude that the mixed neutralino and axion dynamic scenario is the best in the region of FA around 10 to 12 GeV. So we may hope to find both of them. And so if we take Axino as the LSP, then again Axino decay signature is interesting. So this is another opposite limit of regional particle space where we can also constrain the natural SUSY parameter mu and the HIPM scale through the displaced vortex searches. Thank you.
Let's thank for a very nice seminar and also for a very nice introduction. Any questions at the beginning? I have a question to start with. In the case that the Axino is not found, so then what is the so you will what do you think about the superpolation in the MSSM? So is that, in other words, how essential it is that matter constraint?
Yeah. I mean,
one of the nice things is that can be tested.
actually, it's impossible to rule it out.
Yeah.
You know, I mean,
So let me put it this way. When would you give up?
okay, yeah, that's a fair question.
A bit more, aggressive. What it would be for you is striking, saying that some model doesn't work.
Yeah. Okay, bicep is important. So if bicep is confirmed, so I would stick to the standard scenario, saying that, say, PQ scale is more than 10 to the energy, say, operators 10 to the energy. And then from collider side, actually we didn't do this consistent I mean, our heavy Axino paper was done before bicep too. So it all depends also on cosmological action models.
Right.
So combining this bicep 2 with this so-called natural Suji region, we may have some different regions. So.
So that has not been done yet.
Yeah, it's not.
Okay.
It's not. So, well. Then also it depends on whether we find the Higgs and the WIMP down narrow and so on. So no, I wouldn't give up. I mean, so I mean, basically it's hard to rule it out completely. But okay, so. But it doesn't appear any sign of this in, I don't know, in menus. Of course, it's very tiring. So it naturally dies away. So I don't have to give up. I myself lose interest. But exciting stuff is that when there is one positive signal, which indicates, I mean, which I talked about in this talk.
Right, so maybe
but of course, in that case, we are not sure whether this is really from Axino.
Exactly, yeah.
But,
if
but assuming that is from Axino, we can start to constrain the axion country space. So that will be interesting.
So, I mean, there are other questions? Or? Because I do have many, but I think it's good to. Yeah, so another question I have is about gravification. How this model actually fits within the gravified scenario.
I mean, if you are asking about the presence of infinite scale, which is different from gravification.
And how this sets up, I mean, how that emerges.
Then again, this has to be put by hand.
There is no.
And then in terms of, say, apart from that, you can just have both.
So just combine with
God
an
plus,
extra U1 at the end.
PQ.
But it's mostly it's put by hand, it's not a mechanism in that.
Actually, the PQ sector is put by hand. You have to put by hand is anomalous symmetry and symmetry breaking scale. So, of course, there have been some efforts to generate this PQ scale from some other parameters in the theory. So model dependent.
Because one thing you did not mention, but we discussed a little bit, was about the D minus L. I mean, the production, for example, the baryon symmetry. Does this model help in baryon symmetry or not really? Because you have possible sources of CP violations, of course.
Oh, well, you mean?
So you try to solve the action, I mean the third angle of the Solar model,
Right.
but the still the production of the antibodies, sorry, the proton process. Whether actually you have any relation with that?
Yeah. So recently there was a paper by somebody. I mean, basically, yeah. So people try to use this strong CP to generate baryon symmetry between, but it didn't work basically. So then, actually, nobody tried to connect this strong CP with the baryon symmetry.
Okay, but what I can get from your talk is to say that natural SUSY does not have a dark matter candidate on its own. So you need to extend it in any case.
Yeah.
And by adding the axion or from the axinos, basically, it is now a possible source of dominant dark matter there.
Yeah.
So this is actually, so in other words, the SUSY MSSM per se doesn't do it. I need to extend it. And there's not a single component, but a multi-component dark matter.
Yeah.
In that sense, one has to go beyond the minimal
Yeah.
dark matter scenario. So in any way, is there anything that you could consider particularly as a smoking gun for this kind of theories? So what would actually be considered as smoking gun? I mean, assuming that none of the standard superpartners are seen basically so treated like neutralinos, because in this natural SUSY they're pretty hairy, right?
Nice, again, difficult question.
Yeah, we're pretty to solve
Yeah, this is, the theoretically interesting. I mean,
No, I mean, maybe some easy, maybe some specific
venue,
process.
but smoking gun is hard. Yeah, everything is pretty much model dependent.
Okay,
So
so there is actually
it's
very hard to
really,
actually.
yeah,
Okay.
really.
But it's also fair. I mean, it's good to be ignorant because I mean,
Yeah.
it means Lucy can have a job. So,
And maybe one way to put this question is like to reverse it and say, what signal of new physics would actually rule this out? As in, it would hint to something else, to another explanation for this thing.
Yeah, that's right.
If they see some excess in which channel would you say, okay, so this is probably not realized because there should be something else which I cannot put in my description.
Yeah, that's good way of. No, I didn't think of it seriously. But anyway, if we consisting of 100% of diagonal component, then of course the axion is ruled out. So axion is minor, but still axion can be 10%. Yeah, I don't know.
there are
But yeah, anyway, I think it's interesting to think about the possibility.
you have basically a week, part of the week in any case, to ask more questions. Because I mean, there are a number of things that are interesting to understand in any case. So, let's thank you again.